right, guys, by now you should have completed your do now. And today we are going to do our instruction pre recorded. I know, right? It's like having Miss Williams, but not having Miss Williams at the same time. Right. Anyhow, today we will be talking about the scientific method. And what you will need is the slideshow that I will be attaching to the team's classroom. You will need your OPVL descriptors table that gives you all of the questions on the OPVL chart, as well as your blank OPVL chart. So, see you in a bit. All right, everybody. Today we're going to be talking about the nature of science and the scientific method. The nature of science and the scientific method. So we want to remember our student expectations. The first expectation is the students should remain on mute unless Ms. Williams calls on them. Students should have their cameras on at all times. If students have a question, use the chat box to the left to send Ms. Williams messages and wait patiently, especially during class because I'm probably teaching you. Also, always have your quizzes account up and ready for quizzes. Super important. We don't want you to be left out. Always have your packet ready to plug in your answers and raise your hand on your team screen when you go to the restroom or step away, and lower your hand when you are done and you have returned. All right, so the vocabulary to look out for will be data, experiment, independent variable, dependent variable, and of course, your hypotheses. So let's talk about misconceptions. Misconceptions are things that people assume are true, but haven't really done the research or tested to know for sure. So the common misconceptions that we usually see about experiments are, number one, people think that you only need to test the experiments once. And that's not true, because just because you get a result one time, if you do it again, you may not get that same result. So you want to test it multiple times. The second misconception, or things that people get wrong about experiments, is they think that the same data or information that we collect can be used for everything. We gave an example in class. If we were talking about cats, we couldn't use information about dogs to talk about the cats because it won't apply to what we're talking about. So we want to make sure that we're collecting new data every time we're doing a different experiment or approaching a new scientific question. The next is, science vocabulary isn't needed. I don't need science vocabulary. I'll be just fine without it. That is a misconception, because if we don't use the vocabulary when we are doing our experiments, or when we are writing down our observations, or when we are asking scientific questions, then when we get ready to test and we see that question and they're using the vocabulary, we can't figure out what the question is asking. So we want to make sure that we are using scientific vocabulary. And last but not least on misconceptions is, you don't need to know exactly how each variable affects the experiment. That is 100% wrong. And we're going to explore today what each variable does so that we don't make these 4 common mistakes that people make whenever they're doing an experiment. So what is science? Science is a way in which answers related to natural events are proposed. It is a way in which people can learn and understand events in the natural world. We're able to explore science based on observable events. When we talk about observable events, to observe something means to be able to see it, touch it, feel it, smell it. We take events that we can see, we use artifacts, and we use materials that we can touch, feel, and smell in order to explore scientific events or natural events. Study naturally, of course, is the study of the natural world. And since we are putting all these practices into action, we have a specific method of discovery and understanding by using a problem-solving process. And that problem-solving process is called the scientific method. We use a method of discovery and understanding by using a problem-solving process, and that problem-solving process is called the scientific method. So, I want you to take a few seconds And I want you to come up with your own hypotheses and then tell the class how you would test to know whether your answer is true or not. You want to pick a hypothesis that you can test from home and what materials you would need to do the test. But of course, you're asking, Miss Williams, what is a hypothesis? A hypothesis is an educated guess. It is a guess that you can use your brain power to try to answer. And then after you figure out what your guess is going to be with your brain power, we can use the information, materials, and resources to find out whether your answer was correct or not. An example of a hypothesis is the sun hot? And a way to show how you could test that hypothesis is to say, I will test this by putting toys in the sun and checking the temperature. Seems pretty simple, right? Go ahead and take a few seconds to pause and write down your hypotheses and how you plan to test it from home. All right, moving right along. So there are 6 steps to our scientific method. And those 6 steps are to, number 1, make an observation. Remember, you want to see whatever it is that you're testing. You want to touch whatever it is that you're testing. You want to smell it to make sure that it doesn't have odors. You want to make sure that you are looking at all of the details on the subject or the item that you are studying. 2, you want to form that hypothesis, that educated guess. After you form that educated guess, or you have that question formed, you want to test the hypotheses. Remember when we were talking about on the last slide how you were going to tell us how you were going to test it? That's what we want to think about in step 3, how we're testing it. But most importantly is number 4. Oh my goodness, I cannot stress enough how important number 4 is. We want to collect, organize, and analyze the data. What does that mean? Collecting your data. Looking at that OPBL table, making sure you're able to answer all the various questions on that table to assure that you have collected enough information. Once you have the information that you want to collect, you want to organize that information. Okay, well, if I'm asking questions about who created it and all, and who did the research first, I'm going to organize that, and that's going to go under my origin section. And then you want to do the same thing for each of the other categories on your OPBL table. After that, you want to analyze the data. Analyzing data, 2 huge words. Analyzing means to kind of make sense of what you have found. Looking to see if what you said really ended up being what the experiment showed you. Did the information that you collect support your answer? Analyzing is taking a deep look at all of the information that you collected and organized to make sure that it actually goes with your experiment. And remember, data is simply the information that we've collected while we were doing our research or conducting our experiment. Once you have collected your information, organized it, and then analyzed your data, you want to come to your conclusion. Your conclusion is that decision you made when you were analyzing your data. Did the information that I collect really support my original hypotheses, or did it change after I did my experiment? Once you figure out whether or not there was a change, then you want to back it up, right? Because we don't tell people things and then we can't prove it. So when you draw your conclusion, you're trying to figure out what the proof is going to be after you've determined whether or not the question was truly answered. Once you get to step 6, communicating the results, is writing down your results in a very clear way so that the person who is looking at your experiment can understand what you were trying to say on paper. So when you communicate the results, they should be clear enough to where even if the person didn't see you do the experiment, they could read it and understand. Observations. Observations are usually based on senses or tools. Things like sight, smell, touch, etc. When we look at observations of the natural world, they usually raise questions. Questions like, why did the water rise when the candle went out? Or, research is usually done to help find out more about the questions that are raised, such as, is the sun hot? Well, again, that second bullet is going to trigger us to start researching. Go to Google. Ask Google these questions to help find the answers, because someone may have researched this information first and we can use what they've already collected. Form a hypothesis. Based on your observation, a hypothesis is formed that tries to explain your observation or the answer to your question. Your hypothesis tries to predict or guess or determine the outcome of your experiment before you do it. When you make your prediction, a prediction usually starts with if and ends with then in the statement. For example, if I drop a rock, then it will fall down toward the ground. So if I want to take that same basic question I had, is the sun hot? I would say, if I went to the sun, would it be hot? And then what happens? You would want to explore all of the different components of the hypotheses that you came up with. Now, the thing is, these hypotheses must be testable. So I gave you a catch when I asked you if the sun is hot. How would you test if the sun was hot? Well, you can't really go to the sun. No, but what you could do is sit items out in the sun. Use your observation skills by touching the items to see if they get hot. By smelling the items to see if the smell changes because the temperature has changed on whatever it is that you're testing. And then you can let me know if, based on that item being in the direct sun, does that mean that the sun is hot? So even though it seems kind of impossible, you can come up with an out-of-the-box way to test your hypotheses. When we are testing the hypotheses, controlled experiments are used to test the hypotheses. A controlled experiment is an experiment that tests only one factor at a time. They're able to test one factor at a time by having a control group. A control group is compared with an experimental group, and the other variables are not changed in the control group. What does that mean? You have one group that has no changes to it. So you're gonna have, if we were testing the sun and we were testing with a glass of water, the control glass of water would stay inside in a controlled environment where we're controlling the temperature. The temperature will not go up, it will not go down, and the sun would be on the glass through the window because we are controlling the temperature. The other variables would be the glasses that we might sit outside on our back porch, or if we sit a glass in front of our garage in direct sunlight and we're checking the temperature. Those will change, but remember, the control one is the one that we want to control. We control the temperature, so that one would be the one that was inside of the house. The control groups allow you to see if a change in a variable, such as changing the location of where that glass of water is, creates an observed outcome. We want to see how it creates an outcome by comparing and contrasting the different locations that we would have put that glass of water. So the control group, or the controlled glass of water, would be the water in the house. All of the other groups would be the uncontrolled variables. So we would want to compare and contrast with the thermometer. Did the temperature of the water in the house stay the same? Yes, because we didn't change anything, it's the control variable. But what about the water that's on the back porch and that's in front of the garage? Those are going to change, and we want to write down what those changes were. A variable is a factor that changes in a controlled experiment. And we must remember that variables are changed in the experimental group, and they serve as the factor that is being tested. So again, the variable would be the different locations that the water was placed in. So when we talk about variables, we're taking one glass of water and we're putting it outside. That creates a variable. And when we put that one on the front porch, when we take the glass of water that we put outside in front of the garage, that creates another variable. So let's talk about the different types of variables, because there are different types. The first type is an independent variable. An independent variable is the variable that is being changed in the experiment. To be more specific, the independent variable is going to be the locations in our water experiment when we are testing to see if the sun is hot. The independent variable would be in front of the garage is the independent variable, and on the back porch would be an independent variable. The variable that responds to the changed independent variable, or the variable that is being measured, is the dependent variable. The dependent variable is going to be the temperature, or when we take that thermometer and we're checking, that's going to change based on the location of the glass. So when we're talking about an independent variable in this experiment, it is the different locations, because remember, we're changing where we're putting the glass. But the dependent variable will be the temperature, because no matter where we put the glass, we're still measuring the temperature, and the temperatures are going to be different based on the locations. Another example of these variables and how they work are growing plants with different amounts of fertilizer. You can grow the same kind of plant, but if you put different fertilizers on there, you will get different results. Scientists try to design experiments that will clearly show whether a particular variable caused an observable outcome. So we want to know if moving the glass or having a glass in the back of the house or in the front of the house is going to change our observation on whether the sun is hot. If it cannot be observed, then it cannot be tested. So the question arises is, can we test if a comet impact killed the dinosaurs? Why or why not? Well, we couldn't test that because dinosaurs do not exist, and we can't exactly time comet impact. That's something that randomly happens. So it's something that could not be tested. However, when we did the water experiment, we could test whether the sun is hot because we're able to place the glass in the direct path of the sunlight. The next one is sometimes models are used to represent a real object. We use this when it is difficult to control all of the variables, or if it's not possible to test the real thing. Kind of like how we made a modification to the Is the Sun Hot experiment. We can't actually test the sun, but we can test the rays that come off of the sun and the heat that emits off the sun to make that determination. Next, we want to collect, organize, and analyze that data. And as we said before, remember, your data is information that you've collected. Data is defined as recorded observations or measurements that are either qualitative, meaning that you give a description, or quantitative, which means that you actually have a number. So in our experiment with the glass of water, oh my goodness, we have both, because we can feel the glass and see if it's warm or not, but we can also stick a thermometer in that glass of water to see if the temperature changed. And as we write the temperatures down, we now have numbers. So this experiment ended up being the perfect experiment because we get to see what qualitative results we had or the observations we had, such as whether it was warm or did the smell of the water change because it was hotter or cooler. And then we had the quantitative data, which is the information in numbers, because we could say, well, the glass here might have been 76 degrees, but the glass of water outside may have been 102 degrees. We're able to write those numbers down to make it quantitative. When we think about quantitative, we want to think about quantity or having numbers. You want to make sure that the data that you collect and organize and analyze are based on your observations. So it's only based on what you've done. Only based on what you've done. And last, we want to make sure we're utilizing our tools or our senses such as sight, smell, temperature change, etc. Data is organized in tables, charts, and graphs so that it can be more easily analyzed. And we've already started practicing this with our OPBL table to go ahead and organize and analyze that data as we go. The next step is draw your conclusion. Scientists want to decide whether the results of an experiment support the hypotheses. When the hypothesis is not supported or you can't prove it by the tests, the scientists must find another explanation or another reason for what they have observed. That means that no experiment is a complete failure, I promise, because there's always something to learn from it. Even if what you thought didn't happen, we can now explain what did happen and try to make it make sense for other people. All experiments are observations of real events. Next, we want to make sure that we are communicating those results. We must be able to communicate them in the form of a written paper or presentation. This year, we look forward to having it in a written paper and in presentation form when we look at our science fair. Communications helps other scientists performing the same experiments to see if the results of your experiment are the same as theirs. That's why we want to make sure that it's clear, that we've communicated what we thought, that we have backed up whether or not we collected the information that says, yes, this is true, or no, this is false, because then it'll help other people who are repeating your experiment see if they get the same results or not. So, now that we have taken a look at the different steps of the scientific method, we want to look at what a theory is. Theories are explanations for some phenomenon or some events based on your observations or what you saw, smelled, tasted, felt, etc. We want to do this during the experimentation and also during the reasoning. Your theories is basically telling us how many experiments or how many times did you have to do this experiment. It is explaining why we must repeat it and why we must answer that section in the limitations table about did we repeat the results or did we do the experiment more than one time. And we want to make sure that we are able to make a prediction from our theory. So basically your theory is that conclusion, but summing it up so that it makes it very simple and very clean, again, for the person that is looking at your experiment. So let's talk about laws. Laws, like pull me over, like I get in trouble for this. Laws. So when we're talking about laws in science, laws are actually summaries of many experimental results and observations. What's important about laws is that laws are not the same as theories, because laws only tell what happens, not why it happens. So when we talk about laws, generally it's information that we found that other scientists tell us this is what's supposed to happen or this is what happens, but it doesn't explain why it happened, okay? From here, we're going to stop. From here, we are going to stop. I have posted a OPBL tutorial for you to complete your OPBL table. The table that you will be completing today, based on this instruction, is: why is the scientific method important? Why is the scientific method important. You'll be filling out your blank OPVL table that has been sent to your classroom on Teams. Each group has a posted assignment of the OPVL descriptors, which give you that bank of those questions that you can use to answer. And it's going to give you a blank table for you to transfer the questions. Thank you so much for tuning in, guys. I can't wait to see you in live class again, and have a great day.